The ultimate goal of any confidence interval is to have a very high confidence level, 98, 99%, whatever the case is, and a very small margin of error. So we would love to have a very, very small confidence interval, but a high degree of confidence. So how do we achieve this? This comes about by looking at the formula for the margin of error. The formula for the margin of error has three components: sample standard deviation, critical values, and sample size. Now, of these, you can't really control the sample standard deviation very well at all. This is a number that results from your particular sample and you don't have any control over it. So we aren't going to spend a lot of time focusing on the sample standard deviation. It should be obvious to you that if you want the margin of error to decrease, you want the sample standard deviation to be lower, to decrease. You don't have control over that. Your other options are for this critical T star to decrease. And that means you would like to push these values smaller. But unfortunately, this is not so good. And what I mean by that, this produces a lower confidence level. You don't want that T value to drop. Because if that T value drops, you've got less area in the middle, and that is corresponding to our confidence level. So we do not want to do that. And finally, that tells us that the only way for this fraction to get smaller is if the value of n gets larger, a larger sample size. So the most straightforward way for us to achieve a higher confidence level and a lower margin of error is to take a bigger sample. This is completely consistent with the whole notion of sampling. You are trying to extract information from a population. The more information you can extract, the better. Now, in the previous example for IQ scores, we had a sample size of 31. We found that our sample gave us certain observed value for our statistics. We just condense that and call them statistics. And for a 98% confidence interval, we found that the value of mu was somewhere between 99.22 and 112.46. If you were to do this sampling process over and over and build the confidence interval, about 98% of them should contain the proper value of mu. You can never know whether it does or doesn't, but the higher degree of confidence ensures that we will have more likely than not that we will contain it. So what if we want a 99% confidence level? What sample size will we need? We have to assume that the standard deviation is some value. I'm going to assume it's the value of S that I had before. This isn't necessarily going to be accurate, but it's our best guess. So there's not much option that we have other than to use previous information. We are also going to assume that the margin of error is the same. That means we need to calculate what that margin of error is. So you can use your previous information to do this. From earlier, for the 98% confidence interval, we had that n was 31. We found that our sample standard deviation was 15. And by using the QT function in R, we could find that this critical value was 2.457 with some change. I calculated this in the video. So going ahead and computing this margin of error will produce the value that you'd like. And this turns out to be about 6.61935. So these are the values that we are going to have to use in our new calculation. For a 99% confidence level, remember what confidence level means. It says if you were to take the underlying sampling distribution for your sample average, in our case, this is going to be a T30 distribution when we normalize everything. We want to put some boundaries here to say, okay, I want the area in the middle to be 0.99. Where should I be standing so that I get an area of 0.99 in the middle there? In R, you can use the QT function. If the central area is 0.99, that means there's 1% left to split evenly between the tails. And that means that this area has to be 0.005, the same as that. And so the QT function is essentially a percentile function. And we would then tell R, I want everything from this value back, and the degrees of freedom that I'm going to have are 30 here. If I perform this calculation, R is going to find that this is about 2.750. So going through, we now have all the ingredients we need. It's a simple matter for you to reorganize this formula and find that n would have to be the square of this result. If you plug in the values that we had from before, so using the above values, you will find that n is going to be about 38.83. And that means you're going to need a sample size of 39 or higher, because you can't have a sample point less than discrete jumps. And this is consistent with what we see. If you want a higher confidence level, you need more information. If you just took the margin of error formula and kept the sample size the same, the only way to increase the margin of error, the only way to increase the confidence level is to increase this term. But doing that while keeping n and s the same would increase the margin of error. So if you want to increase this but have no change in your margin of error, n must increase to do that. So it's this trade-off. There's one little note that I want to make. The length of a confidence interval is simply the upper limit, so that's x plus the margin of error, subtract x minus the margin of error. This is going to be twice the margin of error. So there are some questions and some calculations where they want to tell you, hey, I want the length of the margin of error to be so-and-so. So some calculations will include statements about the length. So this would be the appropriate formula. And figuring out sample size would then introduce a factor of 2 squared in your calculations. But that's nothing above what we talk about here.